In this chapter, we're going to talk about problems. We're going to talk about classifying problems. And so it makes sense to pause for just a second before we get into that and talk reflect a little bit on the kinds of problems that we're classifying. So we're going to have two videos in this section, and the first is going to be just listing some problems that a person would keep in mind, would recognize by name, and the second part will reflect a little bit on some of those problems. So let's start in. So let's see. Just going to list some famous problems. The first, the Hamiltonian Circuit problem. So given a graph, decides if it contains a cyclic path that includes each vertex once and only once. So let's look, for example, at this graph here, and let me make it a red color here so that's easier to see. So I could go like so by going through that edge, and then like so, and then like so, and then like so, and then like so, and then like so. So I've managed to include each vertex once and only once in a cyclic path. But when I look over here, you notice that if you want to include each vertex once and only once, you've got a problem, because this, like the prior one, is a bipartite graph. There's two halves, and the ones on the left connect only to ones on the right. The ones on the right connect only to ones on the left. But the difficulty is that there's 3 on the left, only 2 on the right. So for every over, there's not a back. You know, you can go over, and then over, and then over, and now you're kind of stuck because there's no way to kind of there's no way to go back to here and then back to there. Okay, so the graph on the left here has no Hamiltonian circuit, but the graph on the right does. Okay, so that's an example of a famous problem that a person would know right away if you're listening to a talk on computational complexity. Oh yes, the Hamiltonian circuit problem. I remember that one. A special case of the Hamiltonian circuit problem is the Knight's tour problem, which is the idea there is to use a chess knight to make a circuit of all the squares on the board. So what's happening here is that we have the first place where we put the chess knight, and then do you remember how chess knights work? It's over 2 and up 1 is an example of a chess knight move. Another example is over 2 and down 1 kind of stuff. And so what you see here is that on this graph, we're able to visit every square on the board, every vertex, once and only once. This is a chessboard, once and only once by making a sequence of chess knight moves. So in graph theoretic terms, there's 64 vertices, and an edge goes between 2 vertices that they're connected by a single knight move. And then Knight's tour, the Knight's tour problem asks for a Hamiltonian circuit of that graph. Okay, another example along the same lines is the very famous traveling salesman problem, and it has been my experience that everybody's heard of the traveling salesman problem. The basic idea is I've got a picture here of the 48 contiguous United States, and you've got to travel between the capital cities of those 48 states in some way that uses a minimum number of miles. What I've drawn there in the picture is actually the Hamiltonian circuit that actually is the minimal traveling salesman solution. Okay, today computers are so fast you can easily do the computation, but the idea is that you're given a weighted graph where the weights are the distances between cities, and the vertices are the cities, and the weights are the distance between the cities, and you got to find the minimal circuit among all the cities. So as stated, this is an optimization problem. I'm trying to find the minimal one. But we can recast it as a decision problem. So you introduce a threshold bound, a B, say B equals 16,000 kilometers. And you change the problem from find the minimal length circuit to decide if there is a circuit of length less than B. Now, if you could solve the problem, decide yes or no, if there's a circuit of length less than B, then you could solve the minimization problem, because look, you just say decide if there's a circuit of length less than 1. I mean, obviously there isn't. Decide if there's a circuit of length less than 2. Decide if there's a circuit of length less than 3. At some point, you'll get a yes. So if you could solve the decision problem At some point you'll get a yes, that's the minimum distance. Okay, so if we have an algorithm to decide the decision problem with the threshold bound b, then we have an algorithm to find the minimal, the overall minimal circuit of all the lower 48 states. So of course we added a little bit of computation to it, but just one loop. So for example, if we can solve the decision problem in polynomial time, then we can solve the optimization problem in polynomial time, for example. So there's a trick there, there's a technique to turn optimization problems into decision problems that we'll talk about more later. Here's another example of a famous problem, the Euler Circuit problem. Whereas Hamiltonian Circuit, the idea is to touch each vertex once and only once, and if it so happens that there is an edge, you don't go through that edge, no problem. With Euler Circuit, it's the exact opposite. You want to touch each edge, you want to traverse each edge once and only once, or declare that you can't. So this is the picture of the city that Euler did. Again, Euler Circuit problem is one that I find that people have always heard of. You really can't see it all that well, but there's a river here, and it goes around an island, goes around an island, and goes around the island. There we go. When Euler wrote his paper, he drew a picture of that tries to take some of the clutter out here. And so this is Euler's original picture. And you see there 2, 3, 4, 5, 6, 7 bridges. And you can simplify that 7 bridge drawing even more to get the area here. This is called area A, area B, area C, and area D. And so I shrunk the land masses down to just single points, and the bridges are edges. And the question is, can you traverse can you find a circuit that traverses each edge once and only once? Okay. So just doing some famous problems so that when we later on talk about problems and we say, well, this is an example of the Euler Circuit problem, you say, okay, I remember that one. Another example of a famous problem that will come up all the time is the shortest path problem. You're given a weighted graph. There's a graph with edge weights, 15, 5, 30, 20 kind of thing. And you're asked to find the shortest distance between V0 and V7. Okay, or maybe you'll report that in fact there is no path between V0 and V7. Okay. Well, it turns out that there is, of course, an algorithm to solve this, a very fast algorithm to solve it. And in fact, the existence of a fast algorithm to solve this problem, you can see it in red here. Can you see it? I wrote the numbers a little larger too for a person who has some trouble seeing red. So 14, 18, 2, and 16. So there's an algorithm that solves this problem. A Dijkstra's shortest path algorithm, for example, solves this problem very quickly. And the fact that there is a fast algorithm to solve this problem, in fact, I want to point out before we leave this picture, in fact changes the world. The fact that there is a fast algorithm to solve the shortest path algorithm means all kinds of things are possible that were not possible before. So classifying problems as quickly solvable or not quickly solvable is an immensely practical thing to do. Some more graph problems, just tried to group the problems together in some way, and I didn't want to do alphabetical, so I grouped them into graph problems first. So some more graph problems are graph colorability. Given a graph and a number k, decide whether the graph is k colorable. That is, can we partition the vertices into k many sets where there are no two same set vertices are connected. And the related problem is, given a graph, find the smallest number k such that the graph is k colorable. And it has been my experience in the past that sometimes folks have a little kind of conceptual trouble with what's the point of coloring again. So I have an example. So you imagine that you own a marina, and the marina rents boats. You will have 4 boats that are available to rent out. So today there are 8 reservations. The 8 reservations are modeled here as 8 vertices. So this is the Smiths, this is the Joneses, this is the Robinsons kind of stuff. in the model, the significance of the edges is that if the reservations have overlapping times, then we connect the vertices. So here, whoops, lost my mouse again, there we go. Here, the significance of this edge right here is that the Smiths and the Bakers have a reservation that has an overlapping time. Maybe the Smiths are from 1 to 4 and the Bakers are from 3 to 5. So you clearly can't rent the same boat to both people. So the question is, can I cover this rental scheme with 4 boats? We want to break the reservations into 4 categories in such a way that never do you have overlapping reservations. So we're looking for a 4 coloring, 4 categories to the vertices, a 4 coloring of this graph, and of course I've drawn in a 4 coloring of the graph. You'll find that never is it the case that 2 vertices that are the same color, let me just pick here the 2 light blue ones, never is it the case that 2 vertices that are the same color are connected by an edge. Okay, so graph colorability is about breaking into groups, into categories, breaking the vertices up into categories. And sometimes it's possible to do it with 5, and sometimes it's just not possible to do it with 5. You have to go to 6, sort of thing. The chromatic number question is what's the lowest K you can get away with? So Sudoku, it asks you, Sudoku, familiar example, I think, asks you to construct a 9 coloring of a graph. So you get this graph that's sort of it's presented as an array, but in fact, there are relationships between the boxes, and you're given a partial 9 coloring. The graph has a vertex for each cell, so that there are in fact 81 vertices. And as for the edges, there's an edges between the distinct vertices if and only if their cells are in the same column. You're not allowed to use the same number in both columns. Excuse me, a number twice in a column. Or in the same row, you're not allowed to use a number twice in a row. Or in the same 3x3 grid. So we have a big graph where we've connected the 81 vertices together according to the restrictions of the game, the rules of the game, and we ask ourselves, is there a 9 coloring of that graph? So as you're filling out the boxes, every time you write in a 3, you're coloring those blue. Every time you write in a 4, you're coloring them green. You're asking to break the boxes in the graph into 9 different categories, the so-called colors. Okay, so that was graph problems. I want to talk now about different kind of problems. Satisfiability problem. You're given a Boolean expression and you're asked if it's satisfiable. So if I give you some Boolean expression, how about if I say P and Q, or not R and P, and not P, or not R, or not Q. Okay, so some kind of a propositional logic expression, some kind of Boolean expression, and I'm asked, is there a value for P and Q and R that would make that entire expression come out, evaluate to true? And maybe P is true, Q is false, R is true, whatever it is. In 3 satisfiability, you put some restriction on the clauses. Here are the 1, 2, 3 clauses. You put some restriction on the clauses. You're requiring that each clause has at most 3 variables. Okay, so those problems are ones that will come up as we work our way through and think about different kinds of problems. So here's a worked out example. It so happens that phi there is got clauses with 3 what's called literals in each clause, either a P or a not P, a Q or a not Q, an R or a not R, 3 literals in each clause. And I'm asked, is there a way to make that expression come out to be T? And the most straightforward way to answer that question is to make up the truth table and look on the final column for any T's. And of course you see a couple T's in the final column, so you say yes. Okay, so some more problems with graphs here. Just going to talk our way through what boils down to some vocabulary words. Given a graph and 2 vertices, find if the second is reachable from the first. That is to say, is there a path to the second from the first? Now here I've called that the vertex to vertex path problem. It's a very natural problem. You'll sometimes see that called path. Sometimes see it called something like ST connect. etc. So it goes by different names, sometimes called ST path. So it goes by different names, but here we'll call it vertex to vertex path. Just calling it path alone seems a little bit too, there's an awful lot of path problems. But ST has a disadvantage that the vertices don't have to be named, S and T. But anyway, so I called it vertex to vertex path. That's the way it goes. Minimum spanning tree. You're given a weighted undirected graph. You want to find a subgraph that contains all the vertices of the original such that its edges have a minimal total. Okay, so for example, you're trying to reach out to all the computers in a network and ping all the computers in a network that takes a minimal amount of lag time. Vertex cover, you're given a graph and a bound B. Decide if the graph has a size B vertex cover. There's a set of vertices such that for any edge, at least one of its ends is a member of C. So you're putting down like a penny on enough vertices that every edge touches at least one penny. Can you cover the vertices with a penny for each vertex? Can you cover the vertices in a minimal way, minimum number of pennies, so that every edge touches at least one penny? Clique. Given a graph and a bound, decide if the graph has a size B clique, which is a set of B many vertices such that any two are connected. You know, clique, a person thinks of it in high school, there might be a bunch of people who are all friends with each other. That's called a clique. Everybody in the clique is all friends with each other. So that's what we're looking for. Decide if the graph has a size, say 7 clique. Are there 7 vertices that are all mutually connected? And one more problem here on the list here, just trying to give a person a vocabulary of the kinds of problems we'll be talking about. The broadcast problem. Given a graph with an initial vertex V and a bound B, you decide if a message can spread from V0 to every other vertex within B many steps. At each step, any node that's heard the message can transmit it to at most one adjacent node. So you imagine a computer network, and computers on the network can talk to each other, but at any moment, a computer can only talk to one other computer. If you're here, how long does it take a signal to reach here? If you're here, how long does it take a signal to reach everybody in the network? Okay, so that's the broadcast problem. Oops, I keep losing my mouse. There we go. I'm going to talk about some combinatorics problems here, just running down a list of the kinds of problems. Hope that a person gets a feel for what kinds of problems we'll be talking about. So three-dimensional matching, you're given an input set, you have some x, y, and z, and you look at triples, lower x, comma, lower y, comma, lower z, and you're given an input set capital M, which is a set of triples. Decide if there's a matching, decide if there's an M hat, which is a subset of M, containing n elements, so that no two of the triples in M hat agree on any of their coordinates. So it's not the case that two of the triples in M hat have the same first coordinate. It's not the case that two of the triples in M hat have the same second coordinate. Not the case that two of the triples in M hat have the same third coordinate. Subset sum, you're given a bunch of numbers, a multi-set of natural numbers, given a bunch of numbers and a target, and you decide if some subset of S sums to the target. So I'll write down some numbers here, 41, 52, 74, 37, 56, and 91. And I'll ask, is there some subset of these that adds to, say, whoops, I meant T. Capital T equals, say, 207. Capital T equals 207. Okay? The knapsack problem. You're given a finite set whose elements have a weight and a value. So you imagine, for example, that you're packing for a trip and the things in your knapsack all weigh something. You don't want to carry something that's heavy, and also a value. You want to carry things that are important. So, for example, you might have 7 things, and some of them are heavy but not very valuable. Some of them are heavy and valuable. Some of them are light and valuable. Some of them are light and not valuable. and you ask yourself, can you find a subset S that meets your total weight target, got to be less than a total weight, and also meets your total value target, got to be higher than the total value has to be higher than some bound. And one more here, a partition problem. You're given a finite collection, a multiset A, that has for each of its elements an associated positive number size. You decide if there's a division of the set into two halves, A hat and the complement of A hat, so the total sizes is the same in both halves. Okay, so you might have, say, a collection of 100 numbers, those are the sizes, and you ask yourself, can I divide that collection into two halves where the sum of the things in the first half equals the sum of the things in the second half. Okay, so all those problems have something like the same feel to them. They're all about the different ways in which you can combine things. Games, getting close to the end here of the problems. Seeing a lot of problems, but they all have sort of the same feel to them. Your crossword, you're given a bunch of strings, 2n many strings, and you decide if the words can be packed into a crossword puzzle grid. So yeah, do you ever wonder how people make up those crossword puzzles that are in the Sunday paper? You know, you're given a bunch of words and you're asking yourself, can I get those words into the grid? Well, I have to use this A up and down, this sort of stuff. Here's another example of the 15 game that you may have played when you were a kid. The question here is, oops, lost my mouse again. There we go. The question here is, can I slide these tiles around? Say slide the 7 down and then the 8 over. Can I slide these tiles around so that they rearrange into what they're supposed to be? 1, 2, 3, 4, etc. 5, 6, 7, 8 kind of stuff. Can you do that in a minimum number of moves, or declare maybe it's not possible to do it? You know, maybe you got one that was a trick. Okay, divisibility. So just talking about some various classifications of problems. If I give you a number, let's say the number has 72 digits, can you find a non-trivial divisor? Well, of course, if the number is even, it's not too hard. If the number is multiple 5, that's not too hard either. But suppose that the non-trivial divisor, first non-trivial divisor has 12 digits. I mean, that's a bit of a job. Prime factorization. If you give me a number, can you produce its decomposition into a product of primes? So of course, in grade school, when they ask you for the prime factorization of 72, it takes you a few minutes, but it's not that hard. But if you're given a number with 35 digits, the prime factorization could take you a while. And a related question, a question that you think seems very closely related to the other two, given a number n, determine if it has any non-trivial factors. Don't find a non-trivial factor, just determine if it has any. And of course, in grade school, a person learns some tricks for determining whether a number is divisible by 2, and then that's not so hard, or divisible by 5, that's not so hard, or divisible by 10, that's not so hard, or divisible by 3. Right, surely you learn the trick where if you have a number and you want to know, so have a number say, how about 346? Well, is that divisible by 3? Well, you say 3 plus 4 plus 6, and that's 7 plus 6, that makes, 7 plus 6 makes probably 13, probably. And you say, well, 13 is not divisible by 3. Okay, so we can tell without necessarily knowing much about what the divisibility will yield, we can tell whether the number is divisible. In this case, the answer is no. Okay, so telling divisibility is a little different from producing the actual divisors. So those are 3 different problems, and you can ask about any of those 3 problems. Oh, darn it, went the button 1 too many. In particular, for many years, the consensus among experts was that this was probably a quite hard problem. That probably it would take a very, very long time, that any algorithm you come up with would take a very long time. After all, people have been thinking about composite numbers for centuries, BC type of stuff, long time. But in 2002, these 3 folks, produced a proof that you can do the testing, you can decide whether a number is composite or prime. You can do the testing, in fact, very quickly. and a refinement of their technique, recent refinement of their technique, does the job in time big O of n to the sixth. So actually getting in the practical zone. So this is an example, this last one is an example of a problem where people have changed their mind recently about whether it is quite hard or whether it is in fact a doable problem. That the composite problem, by Cobham's thesis, the composite problem is tractable. As to divisor and prime factorization, nobody knows. Okay, anyway, so we've seen a collection of problems so that when we reflect on problems in the next video, or when we talk about problems in later videos, we'll be able to say, and an example of this is, sort of thing. Okay, very good.